Okay, so now we're going to take a look at example 2.4 from the Active Calculus book. And in this example, we're asked to evaluate the limit as x goes to 0 of sine of x over x using a table of function values. And so one thing that's important to note is if you were just to plug in 0 in for x, then you would get sine of 0, which is 1, and then over 0. So you're getting 1 over 0, which is undefined. So you can't just do the algebra.
Sine of 0, 0.
The sine of 0, 0? Sorry, you get 0 over 0. So you get something that was maybe not well defined here. So it's important that you need to check, to find limits, you need to check points to the left and right of the value that you care about. So we're going to plug in values that get really close to 0 from the left-hand side, which would be negative values. And then we're going to plug in values that are getting close to 0 on the right-hand side. And so in the book, they've already done this, and they said they just plug these values into a calculator. And you can see that these values are getting closer and closer and closer to what value, Katie?
Looks like they're getting close to 1.
Right, right. So like,
because that would be 0.9999999 repeating, which is actually the number 1.
Yeah, exactly. So the idea here is that the limit function is capturing the behavior of the function as it approaches the value x equals 0. It's saying that the y values are getting really, really, really close to 1. And we can verify that with a graph. And if you plug this into a calculator like Desmos, you'll see a graph like this. And if you actually hover over x equals 0, you'll see that the function is undefined at x equals 0. So while the function is undefined, the behavior of the function is going towards the y value 1. Do you have anything you want to add there? Is that okay?
No, I think that's good. I mean, if you were going to try to fill in that point so that it looks like a sort of smooth function, you would put in the value 1. You'd kind of just color in that hole, right?
Right. Yeah, that's a good point. And so that's what's called a removable discontinuity, which is getting ahead of ourselves. Cool.